Hello, everyone. Thank you for joining us. I'm Steve,
And I'm Scott.
and together we are Backyard Musings. We're the Science and Technology channel. Got a really cool update to you today about fusion reactions, stable plasma. For decades, fusion researchers struggled with neutron isotropy, a key indicator of scalable plasma stability. Zap Energy's latest results show its FuZE device avoids the pitfalls of past Z-pinch failures, generating isotropic neutrons that confirm thermal fusion is occurring. A recent Zap Energy study published in Nuclear Fusion presents the most compelling evidence yet that its sheared flow stabilized Z-pinch method produces stable thermal fusion. Would you like to know more?
In physics, isotropy refers to a system where properties remain the same in all directions. In fusion research, neutron energy isotropy is a key measurement that assesses how evenly neutrons are emitted from a device. The uniformity is crucial. When fusion plasmas are isotropic, they indicate a stable thermal plasma that can be scaled up for greater energy production. In contrast, anisotropic plasmas, which emit neutrons unevenly, suggest instability and may not support sustainable fusion. The research conducted on the FuZE device marks a significant milestone in proving that ZAP's approach can be scaled to higher energy outputs, strengthening confidence in the performance potential of the next generation FuZE Q device.
Quote, essentially, this measurement indicates that the plasma is in a thermodynamic equilibrium, explains Yuri Shumlak, SAP's chief scientist and co-founder. Quote, that means we can double the size of the plasma and expect the same sort of equilibrium to exist. Inside a ZAP core, hydrogen nuclei are fused into helium, a process that kicks out a neutron at high energies. These neutrons carry 80% of the energy that comes from the fusion reactor. So, in general, the more neutrons, the better.
However, not all kinds of fusion reactions are created equal. Thermal fusion is ZAP's goal when nuclei are fused together by the extreme heat and pressure inside its plasmas. Thermal fusion produces energetic neutrons that scale exponentially at around 10 to 11th power.
That's big.
Yeah. As the amount of current conducting through the plasma is dialed up to reach the levels necessary for fusion to yield net energy.
Less desirable is what's known as beam target fusion, which happens when a hydrogen nucleus is accelerated to high velocity and strikes a stationary nucleus. Unlike in thermal fusion, beam target fusion indicates that plasma is out of equilibrium and therefore doesn't scale as strongly, making a working energy source much more difficult.
Thermal fusion produces neutrons with isotropic velocities or with the same energy in all directions, while beam target fusion produces them anisotropically, or such that neutrons in certain directions have higher energies. So, comparing measurements of the neutron energy at different locations is a simple way to see how much of the fusion in the FuZE device is non-thermal. Quote, if we saw neutrons primarily from a beam target source, it would mean that our machine wouldn't be scalable. We wouldn't get to net energy production, says Rachel Ryan, a senior scientist at Zap and lead author of the new research.
So this makes sense. I mean, the sun is a big fusion reaction, and there's no magnets around the sun that's making particles go faster and faster and hitting. This equilibrium just makes sense that they're going off in velocities all around in every direction. That makes a lot of sense. So to test the neutron isotropy in FuZE, ZAP scientists and engineers ran a series of tests using neutron detectors placed around the device, measuring 433 plasma shots generated with the same machine settings. The neutrons were found to be almost totally isotropic. Besides being a key benchmark for physics progress, neutron isotropy holds extra historical significance for ZAP's fusion approach. I think it's that almost that once they can get past the almost, it'll be a breakthrough and boom, it'll be there.
Zap is extra conscious of the story its neutrons tell. The company first measured thermal fusion in 2018, and these new tests, done with higher sensitivity and at higher energies, are the latest confirmation that sheared flows can postpone the instabilities that doomed previous Z-pinch efforts. Scalable thermal Z-pinch fusion without requiring any external magnets for confinement remains promising. The paper represents a major physics consideration, Shumlak says. Quote, "This is why we put so much effort into making these precise measurements," he says.
Interestingly, the paper also notes that the neutrons became less isotropic and lost uniformity near the end of each shot. The researchers suggest this is likely a phase where the pinch becomes unstable before it breaks down and stops generating fusion entirely. I think this is the almost perfect, what they were talking about. Understanding that phase may give a better understanding of how to keep the instabilities from cutting fusion short and further increase the duration and performance of the plasma. I think it's exciting. I really do. And I hope they get through that almost and break through with fusion technology. It'll help mankind.
All right. You've heard it here. From where we heard it.
From where we heard it. We're not
Yeah.
experts.
Yeah.
Okay, so if you liked what you saw, click subscribe. Tell your friends, tell your family, and tell your enemies. Check it out. We're the Science and Technology Channel. Thanks
Yeah.
for joining us.
And we'd love to hear your comments. Take care, everyone. Thanks.